morning or afternoon, all my algebra people. Hope you're doing great. Today we're going to be doing something different. So these notes you won't have in your binder, but I've done a couple things for you. One, I've put them on the website. So if you go to the website, it'll say key features of a function or key features of a graph. I don't remember. But it'll say one of those two, and it'll have this entire PDF. Now, in your notes, guys, you have the red 4 pages, right, that are entitled practice or homework, right? You've got those. So today we're going to be working on two things. One, we're going to be working on key parts of a function, but two, you're also going to be working on taking notes from what I have on my screen. Again, it's a tough thing to figure out, but we got to start somewhere, and better to start sooner than later of taking notes from when someone's talking to you or they're showing something, and it's your job to kind of figure out what's important, what's not important, what do you understand, what do you need more help on. So I thought today would be a great day for a video because you can pause this, you can write as little, you can write as much as you need to. So I would have out just a couple blank sheets of paper, and the trick to taking notes is writing out what is important to you or what you think are the main ideas. Obviously any new vocab words. If you learn best from writing out or from having a picture, you should do that. So anyway, we say key features of functions. Really today we're talking a lot about graphs. All right, and there's some new terms that we're going to have today and some old terms as well. So I'm not going to read everything on here. If you guys want to read this, we're all capable of reading. Pause it and read it. What I'm going to do is hit some of the highlights. So to begin with, obviously we see x and y intercepts. Those are not new words for us. We should know where an x and where a y intercept are. And of course we can plot ordered pairs with that. In our table, if you look over here, though, you see that we have x and then we have f of x. Remember, anytime you see f of x, that is the same thing as y. They're interchangeable with each other. Okay, so just remember that. So here, if I input a 0 into my function, right, for an x value, it will spit out a -2. If I input a 1, I get a 0. If I get a 2, I get a 6. And this graph that we're seeing here, guys, is this right here. It is 3 to the x power minus 3, right? So if you wanted to graph that, you could go, hey, I want 3 to the power of x. And if I can write an x in there, and then we're subtracting 3. And this is what this graph looks like. It looks very interesting. All right. We're going to talk about end behavior. You see that word down here. Now, we've done end behavior before, guys, but we've called it something different. And it's not exactly what we've done before, but when we did domain and range, right, and we had to have a graph, maybe here's our graph, and I don't know, maybe it looked something like this. And we said, hey, what's the domain? What's the range of it? Well, we're figuring out what is our graph doing at the very far outreaches, the very ends of our graph. Well, another fancy math term for that is end behavior. So, and we can, I guess, tell you or figure out what is the end behavior of a graph. We haven't changed our graph. So, the graph that we see up here still the same as the graph I see over here. All right. So, interestingly enough, now these graphs are a little bit different in respect because these graphs that we're going to deal with today, while they look similar to ones we've had in the past, have this feature to them right here, and this is an asymptote. It is a super weird word, asymptote. All right, so an asymptote is a feature or part of your graph where it looks like a vertical or a horizontal line. So if we look to our graph here, over here on the right, and I'll zoom in, and you see we've got this asymptote, and it's that green line right there. So an asymptote says, hey, your graph or your function will get very, very close to that line or that number. In this case, this is the number -3, but it will never get there. And while your graph looks like it might, it will never entirely get to -3. So we would say, hey, you have an asymptote at that value, right? And these are just horizontal or vertical lines. So in this case, the green line is our asymptote, and we would recognize ooh, that there's an asymptote at the line y equals 3, right? So y equals -3, right? If we were to graph that line, it just looks like a horizontal line going through -3. So our function will get very close to -3, but if we had a table of values, like we see right here, it will never entirely get to -3. Like if we had negative, 1,000 or -2,000 or -1,000,000, those numbers will keep getting smaller and smaller and smaller, like we see here, right? We go from -2 2/3 to -2 8/9, and then we go from -2 8/9 to -2 26/27. And if we had, -1,000, we're going to keep getting these -2 and just these fractions that are getting increasingly closer to -3, but we're never going to get there. All right, so again, hard to see from a table, much easier to see from a graph. And sometimes if we don't draw our graphs very well, we might be fooled to thinking that, hey, it really does get to -3. But if we use our graphing calculators or any of the other graphing methods, online methods that we've used before, we'll see that these asymptotes are a little bit easier to recognize. End behavior. I kind of skipped. I got so excited I saw this asymptote here. I wanted to talk about it. End behavior, very similar to some of our other new words today, maximum and minimums. So we're going to say, hey, what's the maximum value? What's the minimum value of this function? Again, function graph. So if we look at our main function that we've been looking at here the whole time, right? So this over here. If we were to ask what is the end behavior of our graph, well, we can look at our end behavior in two ways. And so here's the first way that we can look at it here, and it says y approaches infinity as x approaches infinity. So in other words, as these y values increasingly get larger, what happens to your x values? Right, so what is your domain doing with respect to your range? So as the y values increase, what are my x values doing? Well, they're starting here at 0 and they're growing, they're getting bigger. So yeah, we would say as y approaches infinity, so does your x, right? Because your x values are going to approach infinity. If we look on the opposite side, so if we look down over here, it says, now remember, f of x, same thing as y, right? And I think it's a little bit easier until you get the habit of this. Every time you see f of x, just replace it with y. So as y approaches -3, again, -3 is this green asymptote line down here, right? This line right here is our -3 line. So as our function or as our graph or as our y values approach -3, which we know they're never going to get there, we would have seen that in the table. What happens to our x values? Well, our x values will continue to get smaller and smaller and smaller. But again, doesn't matter how small those x values are, they're never going to give us an output of -3. So as the y values approach -3, our function or our x values approach infinity. Sometimes easier to see on a graph. And if you're faced with a problem like this and you're not sure, use our graphing calculators and zoom out, right, and see what happens. Easier to figure out end behavior from a graph than it is from just an equation or just a table. Okay, so a lot of new words there. Again, if you want to read over any of that, be my guest. There you go. If not, we're going to move on, and a lot of these pages here will just kind of walk us through everything. So if you want to, read from 1 to 2, you can do that. I'm just going to hang out here and answer some questions. So here's our graph right here. We've got 1/2, the number 1/2 to the x power plus 2. These are all exponential graphs, right? We call them exponential graphs because we've got exponents, and our variable is the exponent, which is really scary. We'll spend some time with these later on in the year. But for now, here's our function, 1/2 x plus 2, and this is, right here is our function right here, and this is the graph of our function. So I would say, hey, let's just go over x and y intercepts. Do we see any? Clearly I see a y-intercept. All right, I'm going to see a y-intercept right about here. All right, so right there's my y-intercept. That's going to be at 0, 3. Do I see an x-intercept? Well, not in this graph. Maybe if I zoomed out, we could see it. But I'm going to say this is going to be one of those graphs where we don't have an x-intercept. You know, it looks like I'm going to have, let's focus, I suppose, here on the left-hand side of our graph. So let's focus, guys, just on this part of the graph over here. So let's focus on this. Again, this is going to keep taking this up and outward shape. So what's the end behavior doing here? So as our y values increase, right, our y values are going from 4 to 5 to 6 to 7. So as our y values are going up, what's happening to our x values? So I'll say as y increases, you know, to infinity, what happens with x? Our x values approach. It's very bad handwriting. So as y increases, what are our x values doing? Or think domain here, guys. Where's our domain going? Yeah, our x values are approaching negative infinity. So as y goes to infinity, our x's are going to go to negative infinity. And what about on the flip side of that? So what about with the other part of our graph, right? What about this part here? I didn't have a vertical line at all, but it looks like we're starting to get a horizontal line here. Let me say, you know what? I think here's my horizontal line. It's going to go right through here. This is through the value 2, right? So this is one of those new words. This is an asymptote, right? So we have a horizontal line. If we had a vertical line, that's also the same thing. But here our horizontal line, if we wrote it as an equation, would be y equals 2, right? A-S-Y-M, asymptote. There we go. At y equals 2. And so remember, y is the same thing as f of x. So as the y values approach 2, so as y approaches 2, what are our x values doing? So again, so y values, here they are at 3, and here they are at 2.5, and as those numbers, as y's approach 2, what are the x values doing? Well, the x values are just, you know, they are going way to the right, so they're approaching positive infinity. Okay, so let's see if we answered all of the questions. Where does the graph intersect the x-axis? Well, it doesn't, right? We went over the y-axis. We talked about end behavior. Yeah, sweet. Okay, there we go. Onward we go. Let's see what we get here. Intervals of a function. Interval, we're going to look at specific intervals or domains, if you'd like to think of them as that. And you know, maybe our function is increasing or decreasing, or it's doing something between a particular interval. So again, we've gone back to this 3 to the x power minus 3, right? This is our graph right here. So function 3 to the x minus 3. We're very familiar, guys, with compound inequalities like this. We also have another shortcut way to write compound inequalities. We see that right over here. This is called interval notation. Interval notation. Interestingly enough, we leave out the x. I still have 0 and 5. But then remember, we've used brackets here, but we also have parentheses. Brackets are used anytime we're including a number. Parentheses are used anytime we're not including a number. Again, we can't include infinity. That's a made-up number, so we include all the numbers but up to infinity because, of course, it doesn't represent a number. So if we were going to use infinity, we would use just a parenthesis. So again, this is called interval notation. And so it's really just a shorthanded way to write this instead of writing our compound inequalities that we have. They both mean the same thing. Okay, so don't be fooled if we see either of those. Here we're just talking about an interval. We're saying, hey, on the interval from 0 to 5, right, we're going to include 0. I'm going to go all the way to 5, but I'm not including 5. Right, what is going on? Okay. All right, so let's start to answer some of the questions that it's going to ask us here. So it says, look at the graph, determine the intervals where y is positive and where y is negative. Okay, so I want to know the intervals where y is positive and where y is negative. So where is your range positive, where is your range negative? So let's go with positive y values. So where is your range positive? Let me hop over here. There we go. So again, here's 0. So all of these values are positive, right? All of the values below the origin would be negative. Again, we're just focusing on y right now. And so what is that interval? Okay, so the interval, here we go. So our y values will become positive. Here's our line right here. So all of these are now our positive y values. So what interval is that when we think about x values? So yeah, right here, right here, this point right here, ordered pair 1, 0. So if we have positive y values, you've got to have an x value that's right here, guys, greater than 1. Right, at 2, at 3, at 4, we have a positive y value. Right, if we were at 0, well, I don't have a positive y value. Now I've got a negative. If I'm at 1/2, again, I've got a negative y value. Okay, anything really, any number that's smaller than 1, I'm going to get a negative y value. And we see that right here. So there's your intervals, and you can write them just like that. If you'd like to write them with our new interval notation, we can certainly do that. So if I wanted x values that are greater than 1, well, I'm not including 1, right? And I'm going all the way to infinity. So there would be interval notation, x greater than 1 looks like that. Here, x values less than 1. All right, interval notation says, hey, negative infinity, comma, 1. And again, not including either of those numbers, okay? That's why we're parentheses. If we were including 1, we would use brackets, but we're not, so we're good to go. So there's some interval where our intervals are increasing or decreasing, right? And again, we're just looking at, it's going to say, hey, look at y values, look at x values. Right. If we look at our other graph here, if we think about x values, which are domain, and we talk about, is this graph increasing, is it not? Like, so in other words, are the x values always increasing? Are they always decreasing? Do we maybe see intervals where they're increasing here but then decreasing? Right? If we look at this graph, all right, and again, we read our graphs just like we read a book from left to right, right? And it'll, it'll tell us that. But if we read our graph, from over here, what are our x values doing? Well, our x values continue to get larger, but also what are our y values doing from left to right as well? And while they aren't getting larger very quickly when our graph starts here, right? They start off very slowly. Then they really start to skyrocket and really increase very quickly with respect to our x's. So if we look at this and say, hey, where's our function increasing? Right? Our values for both x and for y are always increasing, right, throughout the entire graph, right? Again, you have to remember, it's where's our graph starting. So my red dot here is not where we're starting. We know our graph goes on forever to the left here, but if we started this imaginary starting point at negative infinity, right, on the x-axis, and we know that we have this asymptote here at, what is this, 1, 2, at negative 3. So we start all the way out there and we look, all of your x values continue to get bigger, all of your y values will continue to get bigger. Right? So we can, we can say that this graph is increasing on a specific interval. Well, in this case, it's kind of odd, but it's increasing from negative infinity all the way to positive infinity. Again, we can't include infinity, so we can write that with just parentheses, not brackets. All right, moving on. Don't worry, we've got 3 more pages, but I'll start to talk fast as we get a little bit more in tune here. So here, again, we've got a function negative. We have 2 functions, I apologize. So we've got the first function, which is an exponential function. Again, I mentioned that earlier. These are ones that have exponents in them. In this case, I've got 1/3 to the x power minus 1. Looks like that graph. The table has a linear function, right? Linear is just anything to the power of 1. So here's my linear function. G of x is equal to negative 1/3 x. Compare and contrast the functions f and g by using key features, domain, range, intervals of increase and decrease, and positive and negative intervals. Sweet. Might help us to have a graph here of g of x. So if you need to, all right, we can graph that. If you just want to take my word for it, that works too. So here is our graph of negative 1/3 x. It's the blue line there. Looks pretty good. Okay, so domain and range, this should just be a quick review for us here. If we think of domain of, we'll do the graph on the left first. Right, so we're going to talk about this, and I'm not going to write it down because I don't have all that crazy room. But domain of that, are there any numbers, any x values that would not be included in this domain? No, they wouldn't be. Right, so our domain over here, we could just say is all reals. Range is a little bit more challenging. Again, I'm going to have an asymptote in here. This has an asymptote at negative 1. So range is, hey, you want all the y values that are greater than negative 1. If you wanted to write that as an interval, you would go negative 1, comma, infinity. I think that works for that. So domain and range, good for that one. If we go over to the blue graph here, domain and range, both of them are just all reals. All reals. Same thing for range, all reals. All right, so good there. Intervals of increasing and decreasing. So where is our function increasing? Where is our function decreasing? Remember, you read it from left to right. I don't just start at the origin and go left and then start at the origin and go right. We read it left to right. So if we think about, zoom in here on our graph. Here we go. So if we think about this graph, where is it? Let's just pretend that we start way up here. All right. Here, I'll stay consistent. Let's say we start way up here. This is the furthest point to the left our graph goes. And what's happening with all of these y values? Well, these are all decreasing, right? Maybe I have no idea what number my graph is up here. Maybe it's infinity or something. Who cares? But these y values keep decreasing. Well, what interval, right? And they decrease. They decrease. Wow, and they're still decreasing here. And then what about here? Right, are they decreasing through here as well? Well, yeah, they are. Remember, there's this asymptote here. So these numbers are still going to continue when we think about y values. They're still going to get smaller and smaller and smaller. They're never going to get to this. This is -1. Right, so I have an asymptote at y equals -1. So if we read this graph from left to right, we know this function is decreasing, right? It's my y values are getting smaller. Well, what domain are they getting smaller on? Well, it's the entire graph. So there's really not any place on here, or any interval, I should say, where they're not decreasing. Right? This is never increasing. Well, what about our other graph over here? Here's our 1/3 x, right? This is our other function over here. Does this ever have a time where it's decreasing, or or increasing? Again, where does it start? Well, let's just assume it starts, all the way over here, and it ends all the way over here. Again, reading left to right and thinking about y values, as it takes this downward shape. This is negative slope, so this one's decreasing as well throughout the entire function. Okay, so I think we've answered everything that it wants to know. Again, if you need to read anything on here, here's this page. If not, we will zoom over to our other page. Here we go. Really zoomed out there. Okay, so again, we've got our function here. And it says the domain of this function. So now we've been given a specific domain from -1 to +2. Yeah, we could list its x and y intercepts. Identify maximum, minimum, range, intervals of increasing and decreasing for this function. Okay, I think we can do that. So minimum and maximum, right? Lowest and tallest points on the graph. All right, so maximum, this is just going to be what I would say is the tallest point on the graph. So can't write today. Come on. Yep, tall. Minimum, I'll just say, is the lowest point. Range shouldn't be too hard. And intervals of increasing or decreasing. Again, this is where we'll spend a little bit of our time down here. But we can look and say minimum, we just want a number for this, kiddos. We just want to know, hey, smallest number, and give that y value to me. So, down here, this is our minimum. That's at -6. Our maximum, all the way up here, that's at 3. So this one has a maximum of 3, a minimum of -6. If we're thinking range, again, lowest to tallest, so minimum to maximum, right? That's going to go negative 6 to 3. So if we were going to write that, negative 6 to 3, are we going to include those numbers? If you look back closely, yeah, those dots were filled in dots. So that means we can use brackets here. So in interval notation, it looks like that. They've written it as a compound inequality all the way down there. Thank you very much. Intervals where it's increasing or decreasing. Again, this graph doesn't go on forever. So if we're looking at it just, from this small, tiny little graph here, it's not a very large graph. Where is the graph increasing or decreasing? So, well, this function is always, if we read it like a book, left to right, this function is always increasing. So we start down here at -1, -6. This graph is always increasing, both in terms of x and y values, until it gets to the point 2, 3. So the question is basically, what interval is it increasing on? Well, that's its domain. So it's increasing from, it looks like, maybe we can zoom in here. So the interval that it's increasing, right, looks like it begins here and ends here. So it's going to increase from -1 to 2. There you go. You could write that as a compound inequality if you'd like, but we're including all of those numbers, and everything's filled in. So there's its interval of increasing. All right, last page, here we go. And you've been very attentive and patient this whole time. Now we're given a scenario, right? It's still just a graph. Piano's being lowered from an apartment that's 18 feet above the sidewalk. The piano descends at a constant rate. Okay, its elevation over time is represented by our graph. Here you go. All right, so linear function here, guys. So linear straight line. Identify and interpret the domain. So domain of this, again, here it is in context. Can I have a domain that's really anything outside of the time it takes from when they started to stop? Not really, because it doesn't make any sense in the context of this problem. So we've got to be a little bit wise about what we do. But if we're thinking x values, it starts here at 0, it ends here at 6. There's your domain. If we were talking range, highest to lowest, right? Our piano starts at 18, it ends all the way down at 0, right? So the range would go from 0 to 18. Again, it doesn't go into negative elevation. We can't have that. It's not like it went through the, ground, nor did it start any higher than 18 feet. So there we go. Identify and interpret the intervals of increasing or decreasing. Well, this function is decreasing the entire time, right? So it's increasing the moment this function comes to life right here until all the way when our function ends all the way down here, right? All of these y values keep getting smaller and smaller and smaller. Well, what x interval is that over? Well, that is over the interval from 0 to 6. Very similar to our domain of this graph. So the entire, and that makes sense when you think about it, right? The entire graph is decreasing. So over that interval from 0 to 6, it's going to be decreasing the whole time. What do our intercepts mean? Well, the intercepts, so our y-intercept all the way up here, at the very top, we've talked about this one. So what does our y-intercept mean? Well, initially our piano starts, hanging out this apartment window 18 feet in the air. So when we start at 0 time, right, we're 18 feet in the air. So that's what 0, 18 represents. Again, time is your x, height, or elevation, I guess they call it, is your y value. So at a time 0, I'm at a height of 18 feet. Well, that's our first intercept. My other intercept all the way down here, right, this is at 6, 0. Meaning at 6 minutes, I'm now at a height of 0. So again, in terms of that problem, that's what that means. What's the range of this function? What does it represent? Well, the range, again, not hard to figure out, just 0 to 18. We talked about that at the beginning. And that just represents the piano's height at any given time. Okay, so I think we hit everything in our notes that you didn't have, that you were making up notes. In here, guys, are some pretty nice practice problems. You might need to use a calculator, so use a graphing calculator. So use any of our means. So there you go. So homework tonight, guys. Let's work on all this. So I know that's a lot, 1 through 24, and I've eaten up a lot of your time. But this is some good stuff here. So I hope you enjoyed it, and you guys have an awesome day.